What's the best way to size vapor compression cycle components? Imagine trying to cool your room with a system that's too small or too big. It just won't work efficiently. That's why sizing vapor compression cycle parts correctly is so important. Let's walk through how to do it step by step. First, you need to understand what each component does. The compressor takes in low-pressure refrigerant gas and compresses it into a high-pressure, high-temperature gas. The condenser then cools this gas, turning it into a liquid by transferring heat to the outside air or water. The expansion valve drops the pressure of the liquid refrigerant, making it cold and ready to absorb heat. Finally, the evaporator absorbs heat from the space or object you want to cool, turning the refrigerant back into a gas. Sizing the compressor depends on how much cooling you need. You calculate the cooling capacity, which is how much heat the system must remove each hour. The compressor must handle the mass flow rate of refrigerant that matches this capacity. For example, a small home air conditioner might need a compressor rated around 5 to 10 kilowatts, while larger systems requiring bigger units. The condenser size depends on how much heat it needs to transfer. You calculate the heat transfer area based on the refrigerant's specific heat capacity and the temperature difference between the refrigerant and the cooling medium. For instance, if the refrigerant is at a high temperature, you need a larger condenser surface to dissipate the heat efficiently. The expansion valve must be chosen to match the flow rate of refrigerant entering the evaporator. It needs to create the right pressure drop so the refrigerant cools enough to absorb heat effectively. If the valve is too small, it causes pressure buildup. Too large, and the system might flood or not cool properly. The evaporator size is based on how much heat it needs to absorb. You determine the heat transfer area by considering the environment's heat load and the refrigerant's properties. For example, a small refrigerator might need an evaporator with a surface area of a few hundred square centimeters, while larger cooling systems requiring larger surfaces. Practical factors also matter. You need to calculate refrigerant flow rates carefully to avoid pressure drops that reduce efficiency. Proper pipe sizing and insulation help maintain pressure and prevent heat loss. Minimizing pressure drops in pipes keeps the system running smoothly and saves energy. Using simulation tools can be very helpful. These software programs model the entire cycle and help you optimize component sizes before building the system. They can show how changes in size affect performance and efficiency, saving you time and money. In summary, to size vapor compression cycle parts correctly, you start with understanding the system's cooling load, then calculate the required flow rates, heat transfer areas, and pressure drops. Proper sizing ensures your system runs efficiently, uses less energy, and keeps your space cool without wasting resources.